Hello everyone. Thank you for joining this session. My name is Mohammad Farajullahi and today I will be demonstrating the features and benefits of ETAP microgrid simulation, operation and control as a cutting-edge solution for modern microgrids. Through this session, we will introduce the microgrid systems, their challenges, and the solutions proposed by ETAP. We will then learn how the ETAP microgrid solution can facilitate simulation and hardware-in-loop testing for microgrid system through various showcases. A microgrid is defined as a localized group of interconnected energy resources and loads. A microgrid can work in conjunction with a main power grid, which is known as grid-connected microgrid, or it can function independently from the main power grid, which is referred to as an off-grid microgrid. Microgrids integrate various energy resources such as solar, wind, and traditional generators, along with energy storage system. This integration enables a flexible and reliable power supplies, optimizing energy usage and reducing dependency on the main grid. Additionally, the ability of microgrid to function independently from the main grid makes it essential for enhancing energy resilience, especially in critical infrastructure and remote areas. At the stage of evaluating a microgrid, various studies ranging from design to real-time operation should be conducted. This process typically involves using different tools for each study, requiring the microgrid system to be modeled separately in each tool, which is inefficient and prone to inconsistencies. Additionally, for realistic and accurate studies of microgrid systems, the microgrid controller used for controlling the assets in a microgrid must be included in the simulation. However, integrating a microgrid controller typically requires a specific hardware-in-loop testing setup, which is both costly and challenging to prepare. ETAP software revolutionized this process by providing an integrated environment where all these analyses, including design and feasibility studies, time domain load flow analysis, and transient analysis, can be conducted using a single model. This integration not only streamlines the workflow but also ensures accuracy and consistency across all the stages of microgrid evaluation. ETAP also addresses the challenge of including the microgrid controller in studies by introducing the digital twin of the microgrid controller in simulation mode. This capability facilitates the development of controller logic, tuning the settings, and evaluating the performance of microgrid controller without the need of a physical hardware. Additionally, ETAP offers hardware for the microgrid controller that can be deployed in real-world microgrids with the similar functionalities as observed in the simulations. ETAP also provides an environment to test the microgrid controller hardware without the need for additional hardware, which is usually required for hardware-in-loop testings. By leveraging ETAP's integrated environment and digital twin technology, customers can efficiently evaluate and optimize their microgrid systems with reduced cost and improved accuracy. The ETAP microgrid controller is based on model-driven technology. User can first develop the functions, tune the settings, and then evaluate the performance through the digital twin in simulation mode. Once satisfied with the results, the developed functions and settings can be transferred to the ETAP controller hardware to run in actual system. The information transferred to the hardware controller includes all the properties and connectivity of the system. The hardware can utilize this information behind the scenes to minimize the work required for configuring the controller. Furthermore, the model-driven approach allows for the utilization of predictive simulation to achieve advanced controlling functions. The ETAP microgrid controller offers several built-in functions to control and manage both grid-tied and off-grid microgrids. The list of functions is shown here. We will demonstrate the performance of ETAP microgrid controller for these functions in a grid-tied microgrid example and also an off-grid microgrid example. Let's first dive into a grid-tied microgrid example and demonstrate the ETAP microgrid controller's performance. This system is a grid-tied microgrid with a utility connection. It includes 1 megawatt of wind generation and solar, as well as battery, fuel cell, generator, and around 4 megawatt loads. Additionally, the digital twin of ETAP microgrid controller is responsible for controlling the active and reactive power of the assets. Besides, the microgrid controller also performs other functions required for microgrid applications such as reconnection, black start, islanding control, forecasting, and any other necessary functions for microgrids. The first case being demonstrated is a rule-based active power control. In this section, the microgrid controller dispatches the active power of the assets for a day with a requirement that the microgrid shouldn't export any active power to the grid and can import from the grid according to a limitation. Let's wait till the simulation is done. Once the analysis is done, we can go ahead and plot the active power of the AC cables for the energy resources, loads, and point of interconnection. Let's first look at the tie cable power to the grid. As you can see, there is only importing power from the grid and no export power to the grid. So there is no negative power and active power import is limited to 2.4 megawatt. Actually, that was part of the requirement for active power control in the microgrid controller. As you see here, the maximum power is set to 60%, which corresponds to that 2.4 megawatt for this microgrid. In fact, the microgrid controller sends the command to the battery to charge at times when there is excessive generation and discharge to limit the import power from the grid to the microgrid for the purpose of peak load shaving. The next scenario is related to the optimal dispatching of the energy resources for one day. In this case, rather using mean emission for active power as was selected in the previous rule-based scenario, optimal dispatch is selected to utilize the time of use electricity price for different times of a day to optimally dispatch the resources and minimize cost of operation for one day. Let's run this case first. When the simulation is done, we can go ahead and plot the active power in AC cables for the optimal dispatch scenario. Let's just maintain the tie cable and remove other assets in the plot. As you can see, there is no export power to the grid and import power to the grid is limited to around 2.4 megawatt. However, what is different here is that the microgrid is importing less power from the grid after 4 p.m. This happens because the battery is being charged before 4 p.m. when the electricity is cheaper and discharged after 4 p.m. for the purpose of peak load shaving, which is more cost effective compared to the previous rule-based scenario. The next scenario demonstrates island and reconnection transitions. This scenario shows how the seamless transition to island mode can happen when there is an interruption in the main power grid. Furthermore, the reconnection transition to the grid is shown as well. Let's dive into the results. At time 10.95, the grid is lost and then the microgrid breaker at the point of interconnection gets disconnected and isolate the microgrid. At this point, the microgrid controller has done the analysis beforehand and shed some of the loads. Besides, it switches the battery to grid forming mode to ensure that the system can have a seamless transition to island mode. After that, it brings the fuel cell and generator subsequently into the system to restore all the loads and runs the system in island mode. Once the grid comes back, the microgrid controller evaluates the stability of the grid in terms of voltage and frequency and reconnects the microgrid back to the grid at the moment that synchronization happens. This example shows how we can fully simulate the island and reconnection transition by using ETAP transient stability module. Let's go ahead in the plot section and try to plot the bus voltage and frequency. The bus frequency and voltage disturbances during all this transition can be shown here. And the performance of all the assets can be evaluated during transition to island mode and reconnection back to the grid. In the next example, we demonstrate the performance of ETAP microgrid controller for an off-grid microgrid. This off-grid microgrid example includes a large solar PV, 2 batteries, a fuel cell, and a conventional generator as a backup. Here, the microgrid controller is responsible for the frequency and voltage control plus black start. The first scenario demonstrates the secondary frequency control in an off-grid microgrid. In typical large renewable microgrid systems, a single device is not responsible for frequency control, and all the assets can contribute to the frequency control. In such a system, the microgrid controller is responsible to redispatch all the energy resources running in droop mode in order to regulate the frequency of the microgrid. Let's go ahead and run this case. In this scenario, we have events to increase the loads in the microgrid. If we plot the frequency of the system, we can see that upon load increase, the frequency drops, and then the asset starts reacting. In fact, the microgrid controller readjusts the asset active power set points to bring the frequency close to the nominal frequency. So this is the job of microgrid controller, to regulate the steady state frequency of the microgrid. Let's plot the battery active power during the load increase event. When the frequency drops, the battery's primary controller immediately responds to keep the frequency stable. As the frequency is below the nominal frequency, the microgrid controller slowly increases the generation of the battery to bring back the frequency to 60 Hz or the nominal frequency. The next scenario is the secondary voltage control. One of the tasks of the microgrid controller in an off-grid microgrid is to bring the voltage to the preferred set point. For this scenario, in a study case, we have defined 3 voltage set points at different times, and the microgrid controller is supposed to bring the voltage at the point of interconnection to different voltage set points. Let's go ahead and run this scenario first. As you can see, each time a new voltage reference is sent to the microgrid controller, it adjusts the voltage at the point of measurement within a few executions according to the preferred voltage set points. In the last scenario, I would like to demonstrate the black start. In this scenario, first the system is forced to go to the blackout mode, then the microgrid controller initiates the black start and performs soft energization using battery. After that, it will bring all the loads and solar generation and energize the system completely. Let's wait till the simulation finishes and look at the results for this case. At 7 seconds, we trip all the assets and force the system into a blackout. At 10 seconds, the microgrid controller first trips all the loads to ensure that the system is fully de-energized. In the next steps, the batteries perform soft energization and increase the system voltage from 0 to 100% with a defined ramp rate. After that, the microgrid controller brings up the loads one at a time and restores all the loads. And finally, the solar connects and ramp up and microgrid is being fully energized. ETAP software offers a real-time digital simulator at the microgrid scale, while the microgrid controller hardware is in the loop. In this setup, ETAP software runs on a PC and simulates a microgrid by performing load flow or transient stability analysis in real-time manner. Then it can transmit all the microgrid controller's monitoring data through a communication to the microgrid controller, while receiving back the dispatch commands and applying them to the network simulation. Additionally, ETAP offers a web-based user client to provide access to the microgrid controller. This setup doesn't need any additional hardware and facilitates and speeds up the evaluation of microgrid system and microgrid hardware controller. Let's return to the off-grid microgrid example to demonstrate the HIL testing using ETAP real-time digital simulator. The first step in HIL testing is to move the microgrid controller logic to the hardware. If we go inside the microgrid controller, in the associated page, there is a deploy button. By pressing the deploy button, a package with MGC file extension is created in the project root folder that includes all the logic of the digital twin as well as the settings, connectivity, and network information. In this microgrid digital twin, there is the setting that can determine the mode of simulation. If it is set to the normal, we will have a pure simulation. However, if HIL is selected, the microgrid will run in real time and communicate the input and output data with the hardware. In fact, communication between the microgrid model and simulated in the ETAP real-time digital simulator and the hardware controller is handled by ETAP Data Hub, which acts as a DMP3 interface. Next, we need to move the deploy file to the hardware controller. The IP address of the hardware can be used to connect to the box. The logic can be uploaded through the maintenance page. In this regard, we need to select the deploy file that was generated by the digital twin in the root folder of the project. As the logic is uploaded, the settings and all the required information are moved to the hardware within a few seconds. Let's return to the microgrid and run the real-time simulation. Here you can see the results of the secondary frequency control obtained previously in the simulation. Let's make the plot live to see the real-time result. By starting the HIL, you can see the real-time measurement of frequency being displayed in real-time mode. In fact, all the input tags of microgrid are sent to the ETAP hardware controller and it processes them with the same logic used in the digital twin of microgrid controller. Finally, it will send the output back to the microgrid. As the simulation continues, we can see that upon frequency disturbance, the microgrid controller will react to it and sends the corrective commands to the asset in order to bring the frequency back to the normal, showing that controller hardware performs the same as digital twin as we saw in the simulation. Furthermore, in the web UI through the diagnostic page, the user can check the status of the controller hardware, the healthiness of the assets, operation mode, heartbeat, which indicates the healthiness of the controller, and execution rate. Additionally, we can monitor the input tags coming from the microgrid assets, and also we can check the output tags sent to the microgrid as output commands of the controller. In summary, ETAP technology can be used to develop the required functions for the microgrid controller. Then the developed function can be tested and validated using the digital twin in a simulation environment. Additionally, the same logic used in the digital twin can be deployed in the controller hardware and being tested by using the ETAP digital simulator. In fact, ETAP microgrid solution provides an integrated environment for customers to efficiently evaluate and optimize their microgrid system. Furthermore, the data-driven technology of ETAP microgrid controller allows the customer to use ETAP hardware controller with the same logic deployed in the digital twin. Additionally, it minimizes the effort to configure the microgrid hardware and tune the settings in the real-time field operation, which saves a lot of money and time for the customer. Thank you for your attention, and please don't hesitate to reach out to us if you have any questions.